Welcome back to our course on memory device technology for AI ML computing. I'm your instructor, Dr. Shubhadeep. So before we move on for today's class, where we will focus on synapses, let us do a quick recap of what we studied the last time around. So in the last session, we explored how the behavior of a neuron, especially the leaky integrate fire model, can be directly realized in hardware. We began with a classical CMOS implementation with capacitor resistors and a comparator, which were used to reproduce this leaky integration and threshold firing. But then we went deeper and we saw that neuron-like dynamics can actually emerge from very intelligent device physics itself. So we showed how in an floating body N plus P, N plus structure, using the single transistor latch effect, we can mimic the charge buildup, and then through impact ionization and subsequently through band-to-band tunneling, you can recreate this leaky integrate fire and reset, auto reset cycle, all with 100% CMOS processes. The meaning of 100% CMOS process, remember, is that we don't need any exotic materials to achieve all these things, and you can just tape out your design with a simple standard CMOS. Then we transitioned into emerging nanoscale devices such as memristors. There we saw that using volatile threshold switching, these devices can integrate the input current, fire when a voltage threshold is crossed, and then automatically reset, all within a single physical device. In this regard, we saw quite versatile 3 different mechanisms: insulator to metal transitions in niobium oxide devices, ovonic switching in chalcogenide materials, and also volatile switching in classical CBRAM devices. All of this had the common feature of having volatile threshold switching, and it helped in integrating small currents and showing spiking behavior. And more importantly, we saw that the firing frequency was controlled by the strength of the injected current. And this enables something called rate encoding, just like real neurons. Finally, we also discussed, as you can see in this slide, the behavior of stochastic neurons. And we looked at 2 main examples which mimic stochastic neurons. First is your GST-based PC RAMs from IBM research, and your MRAMs, which came from ITRI or Taiwan. Here we saw that the neurons do not fire at fixed times. There is some stochasticity involved. This is because there are intrinsic material fluctuations, and these are what are creating these probabilistic spikes, which mimics the randomness seen in actual biological neurons. And this stochasticity, which we saw in detail, is not really undesirable. It actually enables the exploration and noise handling ability, and we will see later even in probabilistic computing. So far our focus has been on how neurons generate and transmit spikes. In today's class, we will move to the other important aspect of brain's computation, that is the synapses. And we will see how synaptic plasticity, the ability of synapses to strengthen or weaken over time, forms the key physical basis of learning memory in biological brain and also future neuromorphic systems. Okay, so this ability of the synapses to adapt is what gives you this unprecedented intelligence that you see in brain and of course in modern day neuromorphic systems. Before we go deeper into synapses, let's do a very brief recap of the biological role of synapses, especially the role of synapses in signal transmission. So as you can see from something that we have already studied few classes before, when a neuron fires an action potential, so suppose this neuron is firing an action potential, it transmits down the axon of this neuron to the synapse. Now, what is this synapse? The synapse is the junction between the so-called presynaptic neuron and the receiving postsynaptic neuron. And at this junction or at the synapse is that the signal is either passed forward, strengthened, weakened, or even blocked. So while neurons are generating these spikes, the synapses essentially are deciding how strongly the next neuron responds to the action potential generated by the presynapse. Okay? And we will see what this is in detail in today's class. So now that we have an understanding from a biological sense, let us shift to what really matters for our course, which is the computational perspective. So in neuromorphic systems, we don't really try to create all the chemical basis of how synapses or even neurons behave, but we focus on the key functionality. So as we described the key functionalities, the synapse goal is fundamentally first to transmit the signal or transmit the spike, and second is store and modify the connection strength between the presynaptic neuron and the postsynaptic neuron. So in this module, we are going to focus on this part of the functionality of the synapse, which is technically known as synaptic plasticity. So plasticity is the ability to tune strength. Remember, what is the meaning of a plastic material? Plastic material is one where you apply a force, and even after the restoring force is removed, it does not return back to its original state. Okay, so there is some memory effect which is involved in plasticity. Next, we will look at two different kinds of plasticity depending on the time scales over which this change in the synapses strength is facilitated. After that, we will spend time looking at something called local learning rules that govern plasticity. Now, since local learning rules are the basis of why we want to mimic biological computation in the first place, therefore, let's do a deep dive into what is the meaning of this very technical term known as local learning rule in synaptic plasticity. So, a local rule basically means that a synapse updates its strength only based on the information available at the exact site. More specifically, it only depends on the firing sequence of the pre and postsynaptic neuron. So if you look at the synapse over here, which connects the presynaptic neuron here indicated in blue color to the postsynaptic neuron indicated here in green color, to change the weight of the synapse, all it cares about is what is the firing sequence between the pre and postsynaptic neuron. It really does not care about what is the overall global tasks. There is no concept of error and there is no external bias or external supervision which is provided to modulate the weight of this synapse. But here is the real mystery of the brain. Though we understand these local rules very, very well at the synaptic level, and that is what we will study in our course, we still do not fully understand how millions of such local adaptations collectively give rise to this coherent global functions like perception, reasoning, and classification. So, while we understand locally what is happening, at a global architectural level, we have very little idea. So, I like to explain this with a very simple analogy. So, imagine an alien species discovers one of our supercomputers and starts to study it. So, what they do is they rip the supercomputer apart and they see that at the basic level, the supercomputer is made up of transistors. And what they start doing is applying different voltages at the transistor, the gate, source, and drain, and they figure out through trial and error how the different voltages change the state of the transistor. And therefore, at the macroscopic level, they may fully understand the transistor behavior and even small logic gates. But without any knowledge of the architecture or the circuit hierarchy or even floor planning, they have no way to understand how millions of these local transistors or the local rules which govern the behavior of a transistor together are able to perform all this complex computation. And this is where our understanding of brain is also. We increasingly understand what are the local synaptic rules, but really we have very little idea in understanding how these local updates self-organize into giving this global intelligence. Okay, so next I want to kind of focus on why, despite having such less understanding about how these local rules lead to global intelligence, why is it still that we want to mimic these local rules in hardware devices? And the reason is even more baffling. The reason is that when we use the similar local learning rules in artificial computational systems such as spiking neural networks, which we will be studying in the last module of our course, these systems are still able to learn and perform complex tasks like classification, pattern recognition, and decision making. So that is the key value proposition. Now let us contrast this with what we saw in our previous module on artificial neural networks. So in ANNs, remember all the weight updates were governed only by backpropagation. How did you do backpropagation? You were solving a global optimization problem. Every weight was being adjusted by computing an error from the output layer and propagating the gradients backwards throughout the entire network. That means each synapse needs knowledge of the network's overall objective or the loss function. But this is exactly the opposite of what is happening in synapses with this local rule. And this is very, very important because despite having a clear-cut idea of what is the global problem to solve, still your spiking neural networks are able to do unsupervised self-driven learning, and this helps in gaining huge amount of benefit in energy efficiency. With this motivation, let us go ahead and look at what is synaptic function, or also known as synaptic plasticity, which forms one of the most fundamental concepts in neuroscience and also in neuromorphic computing. So as you can see in the slide, and we have already discussed this, the ability to tune the synaptic weight. Remember, what is the synaptic weight or the synaptic strength? It is that once the presynaptic neuron fires, how much does it influence the membrane potential of your postsynaptic neuron? That is essentially the synaptic weight. So synaptic plasticity is the ability to tune the synaptic weight purely based on the previous history of pre and post synaptic firing. And as we already have discussed and we will see, the synaptic plasticity is the fundamental basis of all motor function, learning, memory, ability to remember, and also the ability to forget. And although the presynaptic neuron always generates a fixed action potential of roughly 100 millivolts, its influence or impact on the postsynaptic membrane's potential is not fixed. And that is the plasticity that synapses bring into the picture. So a strong synapse produces a large change in the membrane potential, pushing the postsynaptic neuron closer to firing its own action potential, whereas a weak synapse results in a very small shift and possibly very small change which is insufficient to trigger a response. So that in essence is your synaptic weight or strength. Now, before we start looking at how the synaptic weight is changing through the firing of pre and post synaptic neurons, let us do a very quick overview of what are the biophysical mechanisms that are involved in facilitating synaptic plasticity. Now, the entire gamut of biophysical mechanism is very complex, so I'm just giving a very quick overview for the sake of completeness. So it all begins when an action potential travels down this particular axon of the presynaptic neuron, and when this electrical spike reaches the synaptic terminal, it causes a depolarization of the membrane of the presynaptic neuron. When this depolarization happens, it specifically opens up calcium permeable voltage gated channels. So remember, during firing, we saw in neuron, sodium and potassium were important. In the case of the synapse or the synaptic cleft, the important ions is calcium. So the moment this happens, the channels open and calcium ions rush into the presynaptic terminal, which is also known as the synaptic cleft. So the synaptic cleft is here indicated by this yellow color. The calcium is the key biochemical trigger in this process, and it almost acts like a switch that activates the synapse. In response to this calcium influx, the synaptic vesicles fuse with the membrane and they start releasing the neurotransmitters into the synaptic cleft. So as you see, these vesicles open up into the synaptic cleft and the red dotted neurotransmitters are released into the synaptic cleft. Now these neurotransmitters can then diffuse across the cleft and bind to the receptors, which are here marked in green color, of the postsynaptic neuron. And this changes a response in the postsynaptic neuron by changing the potential of the postsynaptic neuron or even the current. And this is called the postsynaptic potential or postsynaptic current. Now here is the link to the synaptic weight. The amount of neurotransmitters that are released from the presynaptic neuron to the postsynaptic neuron is generally known as the synaptic weight. And that is what influences the magnitude of the postsynaptic response. And that is essentially what we define as synaptic strength. Okay, with this brief biophysical understanding, let us move on to looking at the two different kinds of synaptic plasticity. So as I had discussed in the introduction, so depending on the duration over which the affected change in the synapse occurs, this time scale is what enables us to classify synaptic plasticity into short-term plasticity and long-term plasticity. And both are very, very important, as we will shortly see. So first, let's begin with short-term plasticity. So as you can see in the slides, the short-term plasticity is induced by firing of the presynaptic neuron, which we will see very soon, over a very short duration, over only 0.5 seconds. However, whatever was the change in the synaptic weight is quickly recovered within almost 1 or 2 seconds. So the induced change is also very short, and the recovery of the synaptic weight is also happens within 1 second. And because of this particular reason, short-term plasticity is responsible for motor functions. What is motor functions? Suppose you get hit in your hand, you suddenly jerk your hand for immediate perception of auditory and visual information, so on and so forth. And that is why the study of short-term plasticity is also very important, because people are trying to build all kinds of vision, tactile, and even auditory neuromorphic sensors. And this is where synaptic plasticity of the short time scale becomes very important. And as you can see in this diagram, short-term plasticity is primarily caused due to the signal in the presynaptic neuron. From now on, we will see how the weight of the synapse or the strength of the synapse will change depending on the firing sequence of the pre and postsynaptic neuron. And for that, we have removed all the biological complications and focused only on one synapse, and we will see how the weight of this particular synapse changes due to the firing of the pre and postsynaptic neuron. And this arrow is indicative of the signal direction of the action potential which arrives from the presynaptic neuron into the synaptic cleft, which connects the postsynaptic neuron. So as you can see, the firing protocol in short-term plasticity involves only the firing of the presynaptic neuron in very quick succession or bursts of roughly 20 to 50 hertz. Such kind of spiking bursts happen in the presynaptic neuron. What we do is we check what is the behavior in the postsynaptic response. Sometimes we measure the postsynaptic potential or current depending on what is convenient. So in this work, which is coming from a biological system, what you are measuring is the postsynaptic potential. And as you can see, as the first pulse arrives, there is a huge response of roughly 1.75 millivolts. But subsequent pulses lead to a ever reducing response in the postsynaptic potential. And this reduction of consequent pulses when compared with the first pulse is known as depression. Whereas in the other case, if there was an increase in the response as compared to the first pulse, it is called potentiation or even sometimes called facilitation. So the first thing that we notice when there is a presynaptic firing is that what happens to the postsynaptic potential, and in this particular case, it happens to reduce the response of the subsequent postsynaptic potentials, and therefore this is known as depression. Next, what we do is we allow it some time to settle down, roughly 1 to 2 seconds, and then again apply a presynaptic pulse and try to see what is the response of the postsynaptic potential. And what we see is that the postsynaptic potential has almost recovered to the original levels which you had seen earlier. And therefore, we call it short-term plasticity. Indeed, there was a change or depression in the postsynaptic potential, but if you allow for some time to pass, these changes are forgotten and the synaptic weight is restored. So this is one of the ways of understanding short-term plasticity. But there is another powerful way of measuring or understanding short-term plasticity, and this is called pulse-paired facilitation. So let us look at what is pulse-paired facilitation. As the name suggests, in pulse-paired facilitation, a pair of presynaptic pulses with a defined interspike gap delta t is applied at the presynaptic terminal. So the presynaptic neuron fires two action potentials which are separated by a interspike gap in time of delta t. What you do is you measure the postsynaptic response. Now let me show how the postsynaptic response looks like from one of my own papers. This is a device data of one of the artificial synapses that I had made using emerging 2D material devices. So let us see what is happening to the postsynaptic response, or in this case, the postsynaptic current when it's subjected to two pulses. So if the first pulse arrived at 0 milliseconds and the next pulse arrived at around 75 milliseconds. So what you could see is that while the response of the first pulse was roughly 1.25 microamps, and we see that the response to the second pulse was greater than that of the first pulse. So response of the second pulse is more than 1.3 microamps. And this is called facilitation. Why is it called facilitation? Because unlike what you saw in the previous slide, where the second pulse showed a smaller response in the postsynaptic potential compared to the first pulse, here you see there is a short-term potentiation because there is an increase in the synaptic response at the postsynaptic terminal. And next what you do is you go and calculate what is the pulse paired facilitation percentage, which is nothing but the change in the response due to the second pulse minus the first pulse divided by the baseline, which is the response of the first pulse. And then that ratio, if you multiply it by 100%, you get your pulse paired facilitation percentage. Next, what you do is you extend the idea and you repeat the measurement of pulse paired facilitation for different interspike intervals. So this delta t, you keep changing and you start noting down what is its pulse paired facilitation percentage, or how much was there an increase in the second pulse with respect to the baseline. And if you do that, you get a curve which looks something like this, where your x-axis is your delta t or your interspike gap, and your y-axis your pulse paired facilitation percentage. And since we are studying short-term plasticity, the effect of the second pulse on the first pulse reduces as you start increasing the time difference between the two pulses, and therefore you are able to see a exponential kind of decay when you look at pulse paired facilitation versus the interspike distance. And this ppf percentage versus delta t is then fit to a double exponential. Each of these exponentials convey that the ppf is not governed by a single process. After the first pulse, there is some facilitation which decays very quickly, which is measured by your first time constant, and while other changes persist for much longer, which is slower accumulation or even buffering effects. Here I would like to bring your attention back into this very fascinating concept of temporal encoding. So what is temporal encoding? Remember, in your traditional computing, data is only stored in fixed binary values of 0 and 1. However, in temporal encoding, the brain uses timing itself to encode for information, where two spikes of the same amplitude can mean completely different things depending on how close or far they are from each other. And that is very, very clear when you look at pulse paired facilitation. So in essence, while traditional systems read what the value is, the brain reads when it happens, making neural communication far richer and much more adaptive compared to traditional systems. With this, let us move to long-term plasticity. In long-term plasticity, the change in the synaptic strength is not fleeting. It lasts from minutes to hours, and sometimes even up to a lifetime. What triggers this is not just a single spike, but a repeated and correlated firing of pre and postsynaptic neurons, as you can see in this figure. And all of this is responsible for learning, memory, and experience. And this is what will be used in our computational models as well. So let us look at the measurement protocol to explore long-term plasticity. So in long-term plasticity, what you do is first you check at your rest condition before any firing has happened, what is your baseline value for your synaptic weight. You do that by firing one presynaptic pulse, and that gives you some response, as you can see in this black color. So before this firing sequence has happened, the response looks like this. Next, what you do is you allow for this correlated or coordinated firing in both pre and post synaptic neuron to occur. Remember, this is different from your short-term plasticity, where your postsynaptic neuron was completely silent. Only your presynaptic neuron was firing. But in long-term plasticity, even your postsynaptic neuron is firing in a coordinated fashion with the presynaptic neuron. So after this entire firing sequence has been completed, you wait for at least 30 minutes. Why are you waiting? To see whether this coordinated firing gave you long-term change in the synaptic weight or not. And after waiting for around 30 minutes, you fire another test presynaptic pulse so that you can check the postsynaptic response. So the postsynaptic response can either be in green color, which is much more compared to the response that you see before the firing, or it can be much less. So the green curve, where the response is more after the firing than before, is known as potentiation, whereas if the response is lower, it is known as depression. So potentiation means the strengthening of the synaptic weight, and the depression means the de-strengthening of the synaptic weight. And this might remind you of your local Hebbian rule in our introductory section when we were discussing neuromorphic computing. Remember, in 1949, Donald Hebb came up with this empirical rule which says neurons that fire together wire together. What is the meaning of neurons that fire together? It means that if the pre and the postsynaptic neuron are involved in coordinated firing, there is a distinct chance that the synaptic weight will improve and there will be a strengthening or wiring together of these neurons through the strengthening of the synaptic weight. However, this Hebbian local rule does not explain a very important aspect. What about the de-strengthening? How can you explain that the synaptic weight is also reducing? And to get an answer to the two key questions, what explains the de-strengthening or depression behavior and how do you find out the magnitude of the change? We had to wait almost 50 years till the seminal work of Markram in 1997 and B and Poo in 1998, who came up with the theory of spike time dependent plasticity. The spike time dependent plasticity explains that causality or correlation is the key in determining not just whether there is potentiation or depression, but also the magnitude of the change in the synaptic weight. So let us understand what is spike timing dependent plasticity. Let's look at the first case, which is shown in the slides. Here, the presynaptic neuron fires first, and shortly after that, the postsynaptic neuron responds. This means that the presynaptic neuron contributed or helped cause the firing of the postsynaptic neuron. In this scenario, the synapse is as if rewarded with long-term potentiation or an increase in the postsynaptic response, which is also nothing but an increase in the synaptic weight. So, the way the biological system interprets this is that this is a useful or correlated or a causal firing, and therefore it rewards it by saying that this pathway helped in triggering a response, so let me strengthen it. However, in the second case, when you reverse the order, the postsynaptic neuron fires first before the presynaptic input arrives. Here, the presynaptic spike is too late to influence the output, and therefore we can interpret the situation as that the presynaptic neuron did not contribute to the firing of the postsynaptic neuron. And as a result, instead of strengthening the connection, the synapse undergoes long-term depression, shown by a reduced response in red color. And the biological system essentially saying that since in this scenario, the presynaptic neuron did not cause the firing of the postsynaptic neuron, there is no point in investing in this connection. So what is really crucial here is that the spike timing window here is very, very precise. It is only tens of milliseconds, as we will see in the next slide. Within this narrow time frame, the synapse decides whether to strengthen or weaken the synaptic weight. But most importantly, there is no external teacher who's overseeing this process, and therefore it is called a local learning rule, which is purely based on cause and effect in the firing relationships between the two neurons. So the last question that remains is, how much is there a change in the magnitude of the synaptic weight, both in potentiation and depression? And that was also answered by the experimental proof of spike time dependent plasticity from the study conducted by B and Poo in 1998. And on the graph, we can see how the percentage change in synaptic weight entirely depends on the timing difference between the pre and post synaptic spikes. So let me define the change in synaptic weight. The change in synaptic weight is the weight difference after the firing minus before the firing divided by the weight that was existing before the firing. So in this case, the causal firing where the postsynaptic neuron fired after the presynaptic neuron, as you can see, this delta W percentage is positive. a large response after minus a small response before divided by the response before. And exactly opposite is the case when you look at an acausal firing where the presynaptic neuron did not cause the firing of the postsynaptic neuron. And if you look at this particular graph, you see a very important trend emerging. If the delta t is small, that means there is more correlation between the firing of the pre and postsynaptic neuron. There is a strong causality. That means we can say with large degree of confidence that the postsynaptic neuron firing was due to the presynaptic neuron if they are very close to each other in delta t. And as a result, to reward the system, for small delta t's, there is an increased change in the synaptic percentage, which is facilitated by the biological system. And as you move away, as you start increasing the interspike distance, it results in a positive causality, but a weaker positive causality, and therefore the change in the synaptic weight is also reduced. If we try to get the mathematical form of this change in synaptic percentage with spike timing, we see that it fits very well to a single exponential. When delta t is positive, meaning presynaptic neuron fires before the postsynaptic neuron, the synapses strength increases, and that too exponentially with reducing delta t, and exactly opposite is when delta t is negative. So with this, let us conclude our class by noting that spike timing dependent plasticity was a breakthrough not just in neuroscience but also in computation, as it enabled truly unsupervised learning in spiking neural networks, which we will study very soon. But before that, just as we explored the hardware implementations of neurons, we should also examine how synapses and their plasticity can be realized in hardware before we move on to looking at full-scale SNN architectures. Thank you very much for your attention. See you in the next class.